Hi, and welcome back to another episode of Things My Teacher Never Taught Me, but I used to have memorized. Today we're going to be looking at exponents and how to use them. Oftentimes teachers will tell you that, hey, anything to the 0th power is 1, and anything to a negative power is a reciprocal, and anything, when you multiply the numbers, you add the exponents, and when you divide the numbers, you subtract, and if you square something that's already being squared, you multiply, and you're just supposed to memorize this stuff. And you can, and that works until it doesn't. And then you're flipping a coin on a test to figure out whether it's one way or the other. And what I want to show you is how to think about exponents and understand where these rules come from. That way, when you do forget about them, which will definitely happen on that test you're having next Friday, that you can go back and figure out where those rules come from and logic your way through it, which is how math should be, right? I mean, math should make sense. That's how it should be done. So the first thing I want to establish is to talk about some basic terminology. Let's pull up those sleeves. All right, so let's start with the number 3. I don't like using 2 for this because, of course, 2 squared and 2 plus 2 is the same thing. It gets very confusing for kids. Too many teachers start with that. So we're going to start with 3. This is the base. It's just a regular number, and the power or the exponent is this little guy right here, that little superscript. Subscripts like a submarine go below, superscripts like Superman go above. Superman sucks. Anyway, 3 squared. What does this mean, right? That's how you hear this a lot. 3 to the 2nd power, or you hear it like 3 squared. And what is this? What does this mean? And it's not something that's super complicated, but I do want to talk about it because there's so many teachers that just don't tell kids where this comes from, and so many kids don't know it, and it's shocking to me every time. So 3 squared means literally a square of length 3. 3 put on a square. So here's a square, and we're going to say it has length 3. And by length 3, we know that all the sides will be 3 because a square has all the sides being equal. So just from knowing one side, I know all the sides. And if I wanted to figure out the area of this square, hopefully you know this, it's base times height. And I know the base, of course, is 3, and I know the height will also be 3 because, again, it's a square. So if we draw in our little lines here on my graph paper, you can clearly see this is a 3 by 3 square. And 3 by 3 is going to produce an area of 9. A base of 3 times a height of 3 gets us 9. In other words, 3 times itself will get us 9. 3 squared is 9. 3 in a square is 9. So that's where this phrase comes from, 3 squared. Of course, you can call it 3 to the 2nd power. That's totally fine. But that's where this comes from. It literally means 3 put on a square. And I think that's important to know because I see a lot of students say 3 squared equals 6. And that's because I would assume they're thinking 3 plus 3 is 6, right? Or 3 times 2 is what they're thinking, right? And I want you to remember that this isn't addition here. We're not adding 3 to itself. We are multiplying because we're figuring out the area of something. Or in this case, 3 cubed is what we would call this. 3 to the 3rd power. What we're really talking about here is a cube of length 3. So there's our square. I'm going to extend this into the 3rd dimension, going from 2nd dimension to 3rd dimension. And there you have it. There's our cube. That's a really good one. Out of that one. All right, so hopefully I won't screw up these lines too badly. We can get like a little Rubik's Cube thing going on here. Oh, yeah. That's great. Don't look at the top. So 3 cubed means that this is the dimension we're thinking in, 3rd dimension. And 3 is going to be the side length. So base of 3, height of 3, and of course a depth of 3 because, again, a cube has all of its sides equal. So what's the volume here? Well, the volume is going to be base times height times width, which is all the same number. And this is just going to be 3 times 3 times 3. Of course, 3 times 3 we already figured out was 9. So another 3 being multiplied on there is going to give us 27. Just to point out as a side thing, 9 times 3 is 27. And you know that not because you have it memorized, but because you know 10 times 3 is 30. So 1 less 3 would be 27, right? 9 groups of 3 versus 10 groups of 3. Just something to throw out there. Anyway, 3 squared, square. 3 cubed, cube. 3 to the 4th power, well, we don't have anything cool for that because I can't draw anything in the 4th dimension. And it's not just because I'm not a very good artist. It's because visually we cannot see in 4 dimensions. You can find things online that look like a 3D approximation of something in 4 dimensions, kind of how I can draw like a 3D image on a 2-dimensional piece of paper, right, and have it look 3D. But I can't draw it in a 2-dimensional space. Sorry, I'm not capable of doing that. But anyway, that's what 3 squared means and what 3 cubed means, and that's what exponents are. It's take this base number and multiply it by itself this many times. So in this case, I can't draw the picture, but I know what this would be. It's going to be 3 times 3 times 3 times 3. 4 3s, and the number of 3s we're multiplying by, again, multiplying, not adding, right, is going to be 4. So I have 4 of those. And I can do 3 times 3 times 3 times 3 in my head, and I can figure that out. That's fine, but I would rather do this. 3 times 3 is 9. 3 times 3 is 9. And then I can multiply them together. 9 times 9, I know, is 81. So that's what exponents are in a very brief sense. What I want to look at is what else is there? What more can we do with exponents? What weird ways can we confuse you on a future math test? Let's take a look at that. All right, so we already said 3 squared is going to be 3 times 3, right? It's 3 on a square, and we're asking what the area is. And area, of course, is multiplication. So what we're going to do is 3 times 3. And our answer will, of course, be 9. So 3 times itself, 3 on a square, is 9. 3 cubed, we said, was going to be 3 times 3. So 3 squared, but with 1 extra 3 tacked on there. And by tacked on, I mean multiplied on, right? So now it's going to be whatever we had before, but just times an extra 3. So I can do this, or I can just say, look, it's whatever we had before, but times an extra 3, right? And if I do that, 9 times 3 is 27, which is exactly what this is. If I go up to 3 to the 4th power, the same thing will happen. I'll have all the 3s I had before, 1, 2, 3 3s, and then I'll have 1 extra 3 tacked on with multiplication. So it'll be the same thing we had before, 3 3s multiplied together, but 1 extra times 3 on there. So if I just take this answer and times by 3, I'll get this answer. 27 times 3 is 81. We learned that earlier, right? 9 times 9. Okay, cool. And I can keep on doing this, right? 3 to the 5th, 3 to the 4th, or 3 to the 9th, whatever you want. But I can also go down. So when we go up, we're multiplying by 3, right? We're tacking on another 3. I don't want to use the word add on another 3 because we're not really adding, right? We tack on another 3 by multiplication. What happens if we go down? Well, clearly the pattern is 4, 3, 2, 1, blast off, right? So 3 to the 1st must come next. What is 3 to the 1st? And when I ask my students this, they have all kinds of different answers. Some say 0, some say 1, some say 3. But we can follow a pattern because that's all math is. It's just exploring patterns. And we can figure out definitively what this must be according to the pattern we've seen. Well, if we go up, we're multiplying by 3. If I go down, like if we're going this way, starting from here and going down, I'm kind of removing one of the 3s, right, that I had before. So I'm going from 4 3s to 3 3s. And to remove that times 3, I'm not going to subtract it, right, because that's not addition. We're going to do the opposite of multiplication, which of course is division. So as we go down, we're dividing out a 3. And that removes one of the 3s, so we now have 3 3s. 81 divided by 3 is 27. 27 divided by 3 is 9. And 9 divided by 3 to get our next answer, well, 9 divided by 3 is just 3. Looks like our answer should be 3. And if you follow the pattern, we're removing a 3 each time. So if we remove this 3, we get that. So that's 3 to the 1st. Anything to the 1st power will be itself. 5 to the 1st power will be 5. 6 to the 1st power will be 6. A million to the 1st power will be a million. And it's because it's just one of those numbers being multiplied by what? Nothing, really. I suppose you could say times 1, but we won't get into that. Definitely not times 0. Speaking of 0, 3 to the 0th power comes next in our pattern. And again, when I ask students this, they have lots of different answers. And some of them will remember that their teacher told them once upon a time that anything to the 0th power is 1. And that's true, and it's correct. But the question is, why is that, right? That's not really teaching just to say, here's what it is, believe it. What we want to do is we want to figure out if this is true and can we show it. So, following this pattern, going down, we're supposed to divide by 3, yeah? So if we take this answer and divide by 3, well, 3 divided by 3, anything divided by itself is 1. I hope I don't need to prove that to you. 3 divided by 3 will be 1, so our answer should be 1. So why is there a 1 here? Well, I kind of mentioned it a little bit earlier. Secretly, there's always been a ×1 at the beginning of all of this. And of course, that doesn't change our answer, so we don't write it out. But when we get to here, it makes clear sense, right? We're getting rid of all these 3's. And what's left over after we get rid of this last 3 by division? Well, just the 1. And again, that's more of a coincidence. The real pattern here is we're dividing by 3 as we go. 9 becomes 3, 3 becomes 1. We can extend this pattern out further. What if we had negative exponents? Bum, bum, bum! And a lot of kids will say, okay, negative answer, right? Negative times a positive is a negative, and they memorize that, and that's great and fantastic until it's not. We're not really multiplying here. It's an exponent, so it's going to act differently. And I can show you that it's going to act differently because it should just follow this pattern, right? As we go down this pattern, we're dividing out a 3. Well, we don't have a 3 to remove anymore. We don't. But that's okay. We're not really removing 3's. We're dividing by 3's. It just looks like we're removing them, right? That's just kind of the result of division. But here, since there isn't a 3, we're not going to remove any 3's because there are none to remove. We're just going to divide. And you might think, oh my God, what is 1 divided by 3? Get it out and type it in. 1 divided by 3, and you type it in, you get 0.3 repeating, and you write that down, write that down! And you wouldn't be wrong, and you'd have to round at some point, right? 0.333333333, and then you'd stop, right? And that means your answer would not be correct. It would just be an approximation. How about we avoid that? All that typing in, waiting for the answer, and just do what I'm going to show you in a later video, dealing with fractions. Fractions are just division for lazy people. So if you don't know what 1 divided by 3 is, great. Write it as a fraction, and you'll get the right answer. 1 divided by 3 is just 1 divided by 3. It's 1/3. That's it. That's it. Right? And 0.3 repeating is 1/3. And I followed this pattern. So 3 to the negative first gets us 1/3. Wait a minute. I'm noticing a pattern. Doesn't mean it's true, but I am noticing a pattern. 3 to the first is just 3. 3 to the negative first is 3, but flipped. And you know what I mean by flipped, right? Reciprocated. 3 can be written as 3/1 as a fraction, right? And if I flip that, I get 1/3. So it looks like 3 to the negative first is the same thing as 3 to the first, just flipped. Let's see if this pattern holds. 3 to the negative second. Oops, not purple. We want red. Consistency. All right, so what's going to happen here? Well, our prediction should be, it should be the same thing as this one, 3 squared, right? Except it should be flipped, so 1/9. What we should get. Do we get that? Well, when we divide by 3, here's how this happens. 1/3 divided by 3. Whenever you divide, you can instead multiply on the bottom. Division is just multiplication done on the bottom. So if we multiply on the bottom, we get 3 times 3, which is 9. 1/9, which is exactly what we predicted it would be. So it looks like there's this relationship here between 3 squared and 3 to the negative second, and 3 to the first and 3 to the negative first, right? The negative sign. And the negative sign doesn't make it negative, it just seems to flip the number. It reciprocates it. 9 becomes 1/9. 3 becomes 1/3. We can then make a prediction for 3 to the negative third. It should be 3 cubed. Whoops, you can't see that. 3 cubed, which is 27, but just flipped. Well, that's easy. Over 27. And if you look, as we divide by 3, we can multiply on the bottom, right? We multiply 9 by 3 on the bottom, and we get 1/27. So that's all it is. That's all negative exponents are, and that's why it makes sense. It's not some random rule that you just flip these things. That just happens to be the pattern between these numbers. And the reason for that is because as we go down, as we decrease the exponent by 1, we are dividing out this base, dividing by 3 in this case, right? Because all of these are 3's. And as we go up and increase the exponent, we're increasing by whatever the base is, in this case, 3. So we're multiplying by 3. And that's it. That's all it is. And I hope that helps you understand why that is and why this rule happens. You'll see this rule when you're talking about stuff. You'll see like a to the negative first just equals 1/a. And again, all this means is that whatever your base is, if it's to a negative power, you just flip it. That's all. You just do whatever you're going to normally do, and then you flip it afterwards. That's kind of the connection. All right, so what about the rest of the exponent rules? What about those? Let's go to these exponents kind of in the wild, how you're going to see them in expressions and equations, and kind of figure out what to do with things like this. As always, we're going to start with numbers, and then we're going to work our way towards letters. That way you don't lose your minds in the process, right? If we can do it with numbers, we can do it with letters. Trust me. So let's use a different number that isn't 2. How about 5 this time? And let's say 5 squared, which again just means 5 on a square, so an area of 25. The only thing funnier than 24. And we're going to multiply it by 5 to the 4th. Of course, we can do this in a calculator, right? But what if you didn't have one? How could you rewrite this or simplify it, as your teacher might ask? Well, because these are both the same base, we can add these exponents. That's what they're going to tell you, right? And you get 5 to the 6th. But why is that? Why does this equal 5 to the 6th? Well, if you think logically, you can see why. 5 squared, this guy right here, is just 5 times itself twice, right? And then we have a multiplication symbol here. And then let's use 5 to the 4th is just going to be 5 times itself 4 times. All right, pretend you never saw this problem, and all you saw was this. I guarantee you would say, well, that's 5 times 5 times 5 times 5 times 5 times 5 times itself 6 times is just 5 to the 6th. So of course that's what the answer is here. Instead of memorizing that I have to add these exponents when I multiply, which again you can do, think logically, right? 5 times 5 times 5 times 5 times 5 times 5. That's 5 times itself 6 times. So 5 to the 6th is the answer. That's it. What happens if we have a negative exponent? Well, we already said that whatever our base is, it's going to have some power. And if we multiply it by the same base with, some other power, our answer is going to be same base, right? 5, 5, 5. But we're just going to add these together, right? So whatever the two bases are, m and n in this case, we're using variables. We're just going to add them together, and that's going to be what happens here. 2 plus 4 is 6. This is the pattern. So should work the same way for negatives, right? Let's do 4. Let's do 4 squared, which is a fun game to play outside. And let's multiply it by 4 to the, let's get crazy. Go 4 to the 7th. Well, if I just did this, I'd get 9, right? I add them up. It makes sense. 4 times 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 4. I think I did 9 there. 7. 9 fours. 7 plus 2 would get us 9 fours, right? What if I did this? I put a minus sign there. So it's like that minus sign. Let's make it red so we know it goes with the 7. 4 squared times 4 to the negative 7th. What's going to happen there? Well, we know what to do when the powers are positive, right? We just add them up, no big deal. Why do these, when we add them up, give us 4 to the negative 5th? Well, again, you can add them, right? And that's going to get you the right answer. But why does that happen? Well, what really is happening here is we've got 4 squared, which of course is a fun game to play outside, but it's also just 4 times 4. 4 times itself twice. Over here, it's 4 times itself 7 times. However, that negative exponent means we have to flip it, right? So it's going to be 1 over all of that. So 4 times itself 7 times. That's 4 times, 5 times, 6 times, 7 times. How do you solve a problem like Maria? Well, for fractions, when you multiply, you just multiply by the top and divide by the bottom. That's all you have to do. So the stuff on the top is going to be multiplied. So I'm going to get 4 times 4 times 1. And then I'm going to divide by all these 4s. Well, the good news is I already see that I can do 4 divided by 4 and get 1. You can do division and multiplication in any order you want. PEMDAS is a lie. So if I do 4 divided by 4, I get 1 over 1. So those both turn into 1s. They do not go away, otherwise it becomes zeros. That's not what happens. 4 divided by 4 is 1, right? And then I've got another 4 divided by 4, which will be 1. And now I can just do math. 1 times 1 times 1 is, of course, 1. And 1 times 1 is 1. Times 4 times 4 times 4 times 4 times 4. 1 times 5 fours is going to get us 4 to the 5th. 1 times 4 times itself 5 times is just 4 to the 5th. Now, wait a minute. We said we get 4 to the negative 5th, right? Well, if you remember, that's exactly what this is. All it is 4 to the 5th, but flipped upside down, which is this. So this is the same thing as 4 to the negative 5th. Again, the key lesson here, if you haven't watched my fraction video, which is going to come out later, so I guess you probably haven't, is to know that we can multiply by the top and divide by the bottom. That's all fractions are. That's it. Everything in the bottom is going to be dividing, and everything in the top is going to be multiplying. If you see stuff that you can divide out, do it. Makes your math easier. That's not so bad. What happens if we use division then? Because we kind of did that here, right? What happens if we set up a division problem, like we aren't multiplying to begin with? Let's do 6 cubed over, let's do 6 squared. Well, your teacher will tell you that we subtract these exponents when we divide. Ah, yes, memorize that. And that's totally fine. But why do we subtract them? Why is the answer going to be 6 to the first? Well, it has to be. 6 cubed is just 6 times 6 times 6. 6 squared is going to be 6 times 6, right? 2 6s being multiplied. And like I said before, you can multiply and divide in any order you want. There is freedom. Do not be shackled by the chains of PEMDAS. 6 divided by 6, I know that. That's 1 over 1. 6 over 6 is just 1 over 1. And now I can clearly see 1 times 1 is 6. And 1 times 1 is 1. And of course, 6 is the same thing as 6 to the first. So it does look like we subtract these exponents. And the reason for that is because what we're doing is we're dividing away those 6s. We're removing those 6s. Much like we were removing the 3s as we went down, right? We had 4 3s here, and as we went down, we divided by 3. Dividing by 3 got rid of a 3, right? Made 1 less 3 there. So as we divide out these 6s, it starts removing 6s from the top. We're removing 2 6s from the 3 6s at top, and we get 1 6 left over. That's it. If things get crazy and we start using negative exponents for a problem like this, it ain't no thing. This is like the most difficult thing you'll see. Let's do the exact same problem, except we'll make the bottom negative. So negative exponent. Well, using logic, we can figure this out. So I know that the top is going to be 6 times 6 times 6. And the bottom is going to be 6 times itself twice, but it's going to be flipped, right? So we're not going to write 6 times 6. We're going to write 1 over 6 times 6. And this is already, I can hear people through YouTube crying out, oh my God, a fraction of a fraction, what do I do? It's okay, fractions are just division for lazy people. This says take this and divide it by whatever this number is, right? If I just had, that was a terrible rip. If I just had a 2 down here, you would know what to do, right? Take that and divide it by 2, no big deal. Just treat this as one number. It's a weird number, but treat it as one number. We're going to take that and divide it by this. Now, hopefully you know, and if you don't, I'm going to do a quick review, that you can take something like this, 4 divided by 2, and you can rewrite that as 4 times a half. I just took the 2 and I flipped it. If you flip that number, you can change from division to multiplication. 4 divided by 2 is, of course, 2. This is saying we should read multiplication as of half of 4. Well, half of 4 is also 2. It's the same thing, just written a different way. So this double fraction is incredibly scary, right? It's weird, but we can rewrite it. Instead of saying the blue part divided by the green part, we can say the blue part divided times the green part flipped, which is a bit of a mouthful. So I can say the blue part, and instead of dividing, which is what we had before, right? We can say times the green part flipped. Well, the green part was 1 over 6 times 6. If I flip it, I've got this. That 1 down there is extraneous. You don't have to pay attention to it, but if you want to, you can. For fractions, we multiply by the top and divide by the bottom. So I've got 6 times 6 times 6 times 6 times 6. Looks to me like 6 to the 5th. And then we're supposed to divide by 1. Again, you can put the divide by 1 by there if you want, or not. I'm not going to, because I know anything divided by 1 is just for itself. So this is 6 to the 5th, which is exactly what happens when you subtract these. 3 minus -2. Double negative means add, right? You're going to get 5. It's exactly what we got for our power. There's one more thing I want to show you before you go. There's lots more to do with exponents, and I'd like to eventually get out to variables, but for now we're going to keep it simple. And I want to show you one more thing. What happens if we get something like this? Let's say 7 to the 4th, and then it's also being squared. Do not fear. I'm going to pull back the 2 that I used earlier. Fold it up, make it nice and neat. It doesn't take up too much room. All right. If I gave you this, you know what to do, right? It's just 2 squared. Take that number and square it. And you know squaring means 2 times it by itself, right? Because we're thinking area of a square. You could do that. No big deal. 2 times 2. You take whatever this number is and times it by itself twice. All right. Well, take this number and times it by itself twice. This is our whole number. 74th. Ooh. Second time I've lost that red pen. Times it by itself twice. 7 to the 4th times by itself twice. That's all this means. Well, we know how to handle this, right? You probably have the rule memorized by now. But I'll show it again just in case.